Good morning. We are team number 6. My name is Camila Hernandez.
My name is Jocelyn.
Uriel, Arturo.
And we are going to explain our project from math class. I am going to explain the part of the absolute value function and its examples and the function that was given to us, the piecewise function that we are going to solve. I'm going to graphic and I'm going to explain step by step how to do it.
I'm going to explain what is a piecewise function, and I'm going to give two examples.
I'm going to explain the rational functions, I'm going to give two examples, and I'm going to graph the function.
Thank you. Now I'm going to explain to you the absolute value function. What is the absolute value function, or what is an absolute value? It is a function which is represented in an algebraic expression, and it is between both absolute value symbols, which are these two that are two straight lines that have the equation or the algebraic expression in the middle. And these two lines here that are the absolute value symbols indicate that whatever is inside of these two lines that are these symbols automatically make the whatever it is inside. If it is negative, it goes to positive, and if it is in positive, it stays positive. So the algebraic expression is, once it's graphed, it's become in this. So x plus 1 is graphed like this. Its initial points here are minus 1, 1, 0, 0, and 1, 1. This is before the transformation, before we graph it as it says here. And now we have to move it up or down here, which means plus 1 is up. But in this case, we're talking about inside the absolute symbols, which is making the plus symbol to go to the right, sorry. And it is going one space here, and one space here, and one space here. So it turns out that the new points are 0, 1, 1, 0, and 2, 1. And it is represented in a UV form. And its intersections here would be 0, 1 in the y-axis, and in the x-axis it's none, because it is not one space down, or it is not interfering with the x line. And when there has to be a reflection, it's the x. When you want to do a reflection in the x like this, it's minus the symbol of the absolute value and the equation or the algebraic expression. And if you want to do it in y, which is like this, you put the minus and the x after to indicate that you want a reflection in the y-axis like this. So now we're going to do the application problem, which is a function that was given to us, which is, we can see it's a linear function, which is by the mx plus b. The second one is a parabola, which is x squared minus 1. And this one is the absolute value, that is x plus 1. And we're going to graph it right here. Well, it's already graphed, but we're going to know how we graphed it, and we're going to locate and identify which are the empty dots, where are the intersections, and we're going to find out the domain and range. So we're going to start with the first one, which is 3 plus x, but we can see here beside there are some conditions. We have to follow the conditions in order to make the graph so that it is correct and we have a proper answer. So here we're going to start with this one, that 3 plus x, if x is less than minus 3. So here we can see that since it's a linear, it's supposed to go like this. But since we only need from minus 3 to lesser than minus infinite, so we just erase this here, and we just have this point. And since it is not included, it is as an empty dot right here. So this is first one, number, it's A. And now we're going to go with the B, which is a parabola. which is x squared minus 1 if x is greater or equal minus 3, and it has to be also lesser than 2. So here we have the parabola. Its initial points are 0, 0, minus 1, 1, and 1, 1. But since we went from minus 1, it went down, so it went down one space. And it continues from here, but it says we have to stop and it has to include the point minus 3. So we stop here and we put the solid dot. And it says that it doesn't have to go further than 2 positive. So we identify 2 positive and we have an empty dot here. So we already have the B, and we go with the last one, which is C, and it's the absolute value, and that x has to be greater or equal to. So here we identify that this looks kind of similar, but it's actually the absolute value function, which goes like this. But since we don't need the rest of this, why? Because it says that it has to be greater or equal to positive. So when it's greater or equal, it has to be included as a solid dot, as here, as we did here. So we just take this part, we use it as a solid dot, and we just have it from here to infinite, and we have already our graph. Finally, the intersections that we could locate here, it intersects in the x-axis, which is minus 1, 1. So we put it as points here, minus 1, 0, 1, 0. And in the y-axis, which is this one here, it just intercepted here in minus 1. So we just put 0, 1 is 1. And the domain and range, we can see that since here this solid point is filling these empty dots, and as well here, because they're in the same point, they really don't count. So we just take in mind that it's just a single trace. So it goes from minus infinite to infinite, which is the domain. And same here, because it fills this part of here of the graph. So it really doesn't affect there are no unions or whatsoever. So it is the same as minus infinite to infinite. And we already have our domain and range and our intersections.
Well, right now I'm about to explain rational functions. Well, the definition. In math, a rational function is any function which can be defined by a rational fraction. An algebraic fraction such as both the numerator and the denominator are polynomials, just like this one we have here. Well, now I'm going to explain how to graph the rational function, how to get the domain, the range, the horizontal and vertical asymptote, and the x and y intercepts. Well, first, let's begin with the asymptotes. So you already know asymptotes are like HA and BA. Well, if you want to, we can add like these backs and Y. Well, how do we get each one of these? Well, it's actually very easy. In this case, well, the vertical asymptote, we need to take the denominator down here, and we just equal it 0. And now we have to separate x and 3, and it will be something like this. We have both minus x and minus 3, so minus and minus equals plus. So right now, the final result will be this. This will be our vertical asymptote. Now let's go for the horizontal. For the horizontal, we need to look at the x, and we need to look at its number. In this case, we can consider that both are 1 and both are exposed to the 1. Now we have to divide them, but in this case we have this minus x, which will make 1 between minus 1 equals minus 1, and this will be our horizontal asymptote. Now these two we have to locate them in the graph right here. So in this case the horizontal will be here. Here is horizontal in minus 1 in the graph, and the vertical will be here in the number 3. These are our limits in order for graph. This is where our curves are going to bounce back and make, well, the curve. Now that we got this, we can get the intercepts in order to know where our curve is going to finish and go through. So, well, for the intercepts, first let's get the x-intercept. We have to equal y as 0. So in this case will be something like this. Now that it's equal to 0, we're gonna get the denominator to the other side. So we can have something like this. And now 0 plus the denominator obviously equals 0. And this will get us this. So now we can ignore this, and we just have this. Now we simplify, and we have the result. X equals minus 2. So these are x-intercept. Now here in the graph, well, we know how it goes. We can take the line, and we know it goes through minus 2. And there it goes. That's the first one. Now let's go for the y-intercept in order to get the second line. This time the thing we're going to equal to 0, it's the x. So we have y equals 0 plus 2 and 3 minus 0. So we can like nope and nope, and then we'll be left with just 2/3, and that's our y-intercept, where we have 2/3. And now here comes like the tricky part. Well, I did a real mistake here, but suppose that the y-intercept it's like around here somewhere. Well, that through here, because it's 2/3. And well, in the other side, we don't have interception with nothing, so we just do the here. And that's it. Now, for the final, we have to get the domain and range. Well, domain is a CC aspirin x. Goes from minus infinite, comma, to, we are here, it's for this we use the asymptotes that are our lines or walls, we can say. In x we use, obviously in x we'll use the 3, so this goes from minus infinite to 3 parentheses, then union 3 to infinite. So what does this mean? Well, this basically means that it goes from the infinite, alright, to 3 and goes away, and vice versa, arrives with 3 and goes away. Now for the range, it's basically the same. Now it's the horizontal asymptote, which was in this case minus 1. Now we do the same, minus infinite, comma, minus 1, union, comma, parentheses, minus 1 to infinite. And well, basically that's all you needed to know in order to, well, do a rational function. It's pretty easy actually. Well, obviously there are more complicated ones, but this one, it's pretty easy. Well, that was everything. Thanks for watching, and see you next time.
I'm going to explain piecewise function, and a piecewise function is a function divided by multiple subfunctions like this, and each function applying a certain interval. This is our function, and this is our subfunction, and this is our restrictions. So for here, there's a 1, but as it doesn't have an x, we only draw a line in 1. So here is 1, but it says in our restriction that it only goes to 2 without including to infinite. So here it is 2, but without including, so we don't draw the dot, and we only draw a line to infinite. And here in number 2, it says that this is equal to j, so j it will be equal to 2 if x is equal to minus 1. So in number 2 is 1, 2 over here, and minus 1. So we only draw a dot over here. To do the domain, we go to left, to right, negative and positive. So it's domain x belongs to, and we start like here, we don't have nothing, and here is a dot. So it's included, and it's in 1, minus 1. So minus 1, but as it is a dot, that's it. Union with, here we don't have nothing until here in 2. As it's not included, we do the parentheses like this, and it's 2 through infinite. And to the range, j belongs to, we do the same but to bottom to top, negative and positive, and we continue until we see that here we have an empty dot. So we write it like it's not included, so it is in 1. 1 union, you go until here that you have a dot again, but this dot is included, so it's in 2. And that's it.